कैमरा बहुत
और टाइम को एक्यूरेट करेगा वो भी टाइप सवाल पूछना चाहिए बट टाइम को कीप कर रहा है उसकी उसका टाइम एक 12 मिनट के बाद जो 15 मिनट सवाल आ रहे हैं ना उसमें जब लंबी सवाल पूछा तो 1 मिनट के बाद बजर बजा देना अगर इसका सवाल पूरा हुआ तो इसके पास आंसर सुनने की ऑप्शन है अगर इसका सवाल पूरा नहीं हुआ तो जो आंसर देगा उसको बाद में मिलेगा और ये रूल मेरे पे लागू नहीं होता ये सिर्फ लंबी स्टेटमेंट
Good afternoon, everyone. Respected professors, esteemed judges, and all the students and participants present here. I extend a warm welcome to all of you on the second day of the annual Meera Memorial Paper Reading Competition. This event serves as a prestigious platform for undergraduate and postgraduate students to present their research, showcase their analytical skills, and engage in academic discussions. The competition not only provides an opportunity to share knowledge, but also encourages students to confidently defend their work during the Q&A session. As a reminder, the top 3 presentations will be awarded, and we also have a special recognition prize for the best presentation by a first-year student. We are privileged to have Dr. Geetanjali Sethi and Dr. Anu Malhotra as our esteemed judges, along with Mr. Ravneesh Kumar as the student judge. I'll proceed with the competition guidelines once again. Each participant will be allotted 15 minutes, 12 minutes for the presentation, and 3 minutes for the Q&A. The timer will start as soon as the participant begins screen sharing. A buzzer will sound once at 10 minutes and twice at 12 minutes to indicate the end of the presentation time. Exceeding 12 minutes will result in a deduction of marks. The judges' decisions will be final, and we request all participants to patiently wait for the results. Additionally, this session is being recorded. If anyone has an objection to their presentation being recorded, kindly inform us in advance. We also request everyone to keep their phones on silent and to remain seated during the presentation. To start with the competition, I would like to invite Akshay Bhatia for his presentation and ask Samrita Dev to be ready with their presentation.
Good afternoon, everyone. Today, I, Akshay Bhatia, will present my paper on the topic Analysis of Motion of an Irregularly Shaped Satellite. So, the main objective of this paper is to understand the motion dynamics of such a system, also develop a computational model on Python, and analyze to little extent the chaotic behavior in the system. So, let's see if we have satellite of some shape like this, irregular. So how do we study the motion? So let me make a model of a dumbbell consisting of two masses M1 and M2 connected by a massless rod. And I set up a coordinate system by with the planet of mass capital M at the center. So now you can see that it exerts force F1 and F2 on the two masses. The center of mass is here, and I have kept the R1c vector is from center of mass to M1, R2c vector is from center of mass to M2, and RC vector is from planet to the center of the mass. The satellite is also making an angle theta with the x-axis. So first of all, we need to calculate the torque in the system. So, if we calculate the torque and I derive the equation, we finally get the angular acceleration as this. Now to completely analyze the motion, the force is also required. So I derive the equations of force, F1 vector to the F2 vector as this. Now these derivations I use a significant approximation. Approximation based on the fact that R1c vector and R2c vector, if you see here, R2c vector and R1c vector are lesser than RC vector. So based on these equations of force and torque, I get 6 differential equations for my system. And I non-dimensionalize it by taking the following terms. We finally get the non-dimensional differential equation. Now, a very important thing here is that if you can see that the rate of change of this is horizontal velocity and velocity in x direction and y direction, the rate of change also depends on the angle. You can see this cos theta and sin theta term. What this essentially means is that the force on the satellite is not just depending on the distance from planet, but also the specific angle it is making with the x-axis, or in other words, the rotation and revolution of the satellite are coupled, with one affecting the other. But the extent to which they are coupled is determined by this factor, 3 R1c minus R2c, which is multiplied by this. Let me call this factor as A. Now, physically, A is proportional to the size of the satellite, and it also depends location of the center of mass, and is inversely proportional to the distance of satellite from the planet. Let me explain. The capital R1c is basically R1c magnitude upon the initial distance of the satellite from the planet. Similarly for capital R2c. So as the proportion of the size of the satellite to the distance from the planet increases, and also if one mass is greater than the other, the center of mass shifts towards the other. These factors determine the magnitude of A, and as the magnitude of A increases, my rotation and revolution both get coupled together. So I use these equations to analyze the motion of Hyperion, a moon of Saturn. But in that case, we will get revolution and rotation both. But in that case, the A is so small that the effect is negligible. But let's say we think of a system where A is not negligible, that A is significant. So we also need to solve the differential equation for which I use this algorithm. Now let me actually show you my code. So if we actually try to create, so let me run this. Now we need to take some initial conditions. I will keep the initial angular velocity as 0. Initial velocity in x direction is also 0. I will keep the initial velocity in y direction as 1. This is non-dimensional. Step size is arbitrary, depends on the system. You can take any. Let me keep 10,000 iterations. And we need, let's see, want to see the satellite at 1,000 iterations. I will keep the initial angle at 0. Now let us see for different magnitudes of A what happens. So let's see for 4 types of magnitudes. Basically for different magnitudes of A. So now we get some plots. And if you can see, so if A is 0, we get a standard ellipse. Let's say it's not 0. A is 0 meaning, what A is 0 means that satellite is assumed as a point mass, or maybe it's too far. But if A is not 0, we get some strange plots. We get a different motion, the shape is not closed. So the rotation affects revolution and vice versa. And if I also plot the cosine of the angle that the satellite is making with time, we get plots like this, which suggests that the rotation is not standard. It tumbles. Now, I also want to show that this kind of motion is somewhat chaotic. For example, if we change, even if we change the initial condition by a little amount, I will keep everything same. I will just take a different angle. Instead of 0, let us take 0.01 and see. We see for the same factors. So we get plot like we get no plot. Now, because my initial condition was changed a bit, there are some changes. So if I plot, let's say you see that for 4,000 units. Then we see this. So for the two different initial conditions, in the sense that for one the angle was a little different. There is difference in the angle that the satellite is making with time. So if for the both cases, if you actually plot the theta and see for some time the difference between the two theta, there is a difference. And the difference increases as the magnitude of A increases. Similarly, for angular velocity, which means a little change in the initial condition leads to some other changes in the final outcome. And if you see the difference in the distance of the satellite from the planet, so for factor 0 there is no difference over time. Because as I said, for the factor 0 it also like R1C and R2C are 0, rotation is not affected. But as the factor increases, we also see a difference in the distance. This factor of A, we come back. So this factor of A, physically if you want to look at it, it just suggests that how irregular my satellite is. If this size is the proportion of size to distance is somewhat significant, and also if one mass in the dumbbell is more than the other, so the center of mass will be shifted. So if center of mass is shifted, the difference R1C minus R2C becomes greater and A becomes greater. So, but also we need to note that I can't keep increasing A as much as I want. Because in my derivations of the equation, I said that I have used approximations based on the fact that R2C vector and R1C vector is lesser than RC vector. So after some time, this analysis will break down because the fact on which I derived the equations will be refuted. So until that condition is not false, we can see the changes in A. And so basically in this paper I tried to analyze the motion of an irregular satellite and predicting its revolutionary as well as rotatory motion in Python, and the vector A, which determines how much the revolutionary rotatory motion are coupled, and also with increasing A we see that the chaos in the system increases. You can try for n number of different cases. I only showed one, which I just changed the angle by some amount. Now, so these are the some by bibliography and resources I use. Thank you very much.
So, have you used Euler's algorithm for solving your equations?
No, it's not exactly Euler's algorithm. Actually, it is different. Actually, when I did this, I didn't know how to solve differential equations of Python. So I was reading Feynman lecture, and in that volume of chapter 9, Feynman discusses an algorithm for solving differential equations for gravitational motion. So basically, that it is somewhat kind of hard step. For example, if my epsilon is an infinitesimally small time interval, and I need to calculate, if I know x at t, I need to calculate x at t plus epsilon. So I do x at t plus epsilon is equal to x at t plus epsilon into bx at t plus epsilon by 2. So basically the velocity at halfway between t and epsilon, t plus epsilon. So for that I also compute that velocity at t plus epsilon by 2 to kickstart the algorithm I use.
I think that is Euler, but apart from this, the kind of discontinuity that you're showing in your graphs, there are some sharp discontinuities. That should be due to these error accumulation, or there is some reasons for that?
I think in the cos, cosine and theta, I think it's because of the specific equation for angular acceleration also. Because how the rotation is happening and how the revolution also contributes. The rotation is not very well defined. I mean, they will be tumbling and all that. So I think also this can be said the algorithm is also an interpretation, but I also think that this is also an important factor in this computation.
Can you show the distance difference graph?
Yes.
What exactly is it showing?
So this is for the two different initial conditions which I took, that is literally change the angle theta.
What distance is this?
It is the distance of the satellite, the center of mass of the satellite, or from the planet. So over time, if we see for the two cases, when my factor was 0, there was no difference, because the effect of rotation simply drops down. But if factor is non-zero, then there is a difference. So there is some chaoticness which comes in this also.
So there is no order in this change in difference. This is completely random.
I don't know that, but order is one order is that with the increasing factor it is increasing, which we can see. Also it goes down, goes up. I will have to analyze more about it.
Can you solve this problem? तुम बचाते रहो. I don't care. Can you solve this problem analytically?
Analytic. Ma'am, actually.
Just yes or no.
No, ma'am. No.
No?
No.
Go back to your process. No, the way you have to diagram. here. Forget about the mass sitting at the origin. Right? You have a dumbbell which consists of two masses and a rod. Have you taken any mass from the rod? No?
Mass.
It's a massless rod. If you don't have that mass sitting at the origin, can you solve the problem manually?
I don't have the mass sitting at the
Origin. Can you solve the problem manually?
But if I don't have the mass at the origin, the planet is not there.
Forget about planet. If you just have a dumbbell shaped system and give some initial condition, right? Starting with some initial condition, can you solve this problem analytically? Yes or no? That mass that, forget about that this is a planet and a satellite. It's a simple mechanics problem. You have two masses joined by a massless rod, right? I give it some initial condition. Some initial condition. That is, I choose some position at I equal to 0. I choose some velocity at I equal to 0. Can I solve this problem analytically? Okay, doesn't matter. Think about it. I just don't know.
Thank you.
इनका बहुत पीछे चल रहा है तुमने बात ही नहीं समझी
उनके एक्सपेरिमेंट्स बहुत पीछे चल रहे हैं इसलिए वो खुद जबरदस्ती बता एक बार पूछ लो सर से Just I was only waiting that so I was saying that if I still
इसका हमेशा कंस्टेंट
कैंसिल
वगैरह का किसी डिपार्टमेंट के लिए तो कैंसिल
लोग भी लैब में
भी है
बाकी
लैब में लोग एक्सपेरिमेंट्स नहीं हो रहे
इनके आज ही करने हैं सारे आज सारे कंप्लीट हो फ्राइडे छुट्टी होती है ना बहुत सारे फ्राइडे छुट्टी जाते हैं बस ये या जितनी मर्जी क्लासेस दे दो ऑल दी स्टूडेंट्स आर वेरी वेरी फॉन्ड ऑफ डूइंग एक्सपेरिमेंट्स इन द एक्स्ट्रा
अदर
अगर इनको डबल टाइम भी मिल जाए तो फिर भी एक्स्ट्रा टाइम
First years don't have any extra time. That's the इनका कोई afternoon timing नहीं है.
Hello.
I would like to invite Samrita Dey for her presentation and ask Agnes to be ready with her. Hello.
No need to hold, everyone can hear you.
Yeah, can
for the recording.
You need it so that it people can.
I'll take a hand.
What is the problem? What happened?
No,
हमें recording के लिए चाहिए mic.
आपको क्या उसने क्या किया?
because if I have to hold it even when
You can put it on and then.
You just put it around in there.
yeah, but it's not.
That doesn't stay.
It's not really catching my voice. This is fine. Okay. Hello everyone. My name is Samantha. I'm a student at Ashoka University. So today I will be presenting the work that I carried out in the summer at the Institute of Astrophysics. My talk is titled Characteristics of Endoplanetary Shocks at Meera and a Response to Storms and Commencements. I'm going to break that down here. So the aim of our research was to basically create an algorithm to detect the interplanetary shock waves that reach the Earth from the Sun due to coronal mass ejections over the solar cycles 23 and 24, which is roughly the years 1996 to 2023. So we create a database of these shocks and their parameters, and we want to find what effects they have on spatial phenomena at the Earth. So what coronal mass ejections are, they are large plasma expulsions from the Sun's corona, and they travel through interplanetary space. As they travel through interplanetary space, they plow against solar wind, and they basically cause these density waves, which steepen and give rise to shock waves. The theory of it is in a field called magnetic hydrodynamics, but we do not delve into a lot of theory here. My project is mainly communication. So this is how shock wave forms into a coronal mass ejection. When there is a fast CME, it crosses a specific threshold called the Anton threshold, and it causes a shock wave. So yeah, I'm not going to dive into theory. So this is the data that we use for analysis. We use data from the CEDA web, 1 minute resolution data from the wind spacecraft from 1996 to 2024. The parameters that we used to analyze this were magnetic field velocity, plasma density, and plasma diffusion. So this is an example of the raw data, of what the raw data looks like. So what we want to detect here is this shock wave. It's a discontinuity in all the 4 parameters. So our ultimate goal of the algorithm will be to detect this. But there are a lot of fluctuations, as you can see, which are not shock waves, there is fluctuations in the data. So this is basically the algorithm that we created at IIA. I'm going to run through it. So we begin with threshold determination. What threshold determination means here is we assign different thresholds to the 4 different parameters that we are using. So we have magnetic field velocity, density, and temperature. So these thresholds have been created after looking at literature, especially Kirkua, heliospheric shock database, and a paper by Meera. We assign these thresholds to the raw data that we have. This leads to detection of these fluctuations. But as you can see, the shock wave, along with some fluctuations in the data, is also detected, which is not what we want. So we need to refine that further. So we go on to rejection and the merging of candidates. So so as I mentioned, the resolution of our data was 1 minute. So since shock waves are discontinuities, they will evolve almost instantaneously. So we want to reject those candidates whose resolution time period is more than twice the resolution of the data, because that obviously means that those are not shock waves. We also decided to merge detections whose time difference was less than twice the resolution, because that is essentially one shock wave, but our algorithm is detecting that's 2 consecutive shock waves. Once that is done, we move on to refining our detections. To refine our detections, we consider the parameters upstream and downstream of the shock wave. We ignore twice the resolution on either side, and we consider points that lie within 10 times the resolution on both upstream and downstream of the discontinuity. We calculate the median of these selected points. Once we calculate the median, we apply our thresholds on the median again. The same thresholds as well as a different threshold, which is the difference between the upstream and and the downstream median should be at least 50% of the difference between the peak and the base value of the discontinuity. Once this is done, these are our shock waves. Our algorithm is able to successfully identify every shock wave that we usually see in the data. Then we move on to assigning a quality factor to these shocks. So we assign a quality factor of 1 to the shocks that have just passed the threshold. So if there's just a 10% jump in magnetic field, we assign it a quality factor of 1. But if there's a more than 10% jump, we assign it a quality factor of 2. Then we add the quality factors of each parameter and divide it by 4. So our strongest shock waves will have a quality factor of 2. And every other shock wave will have a quality factor between 1 and 2. The last bit is classifying these shock waves. So shock waves are classified into 4 different types. There are fast forward, fast reverse, slow forward and slow reverse. So the different ways in which they are classified is taken from this paper by Meera, and it depends on how the parameters change across the discontinuity. So once an algorithm does this, we also calculate certain other parameters, certain other magnetohydrodynamic parameters of shock waves, that's Mach number and stuff like that. Finally, we move on to verification of results. So the red plot that you see here is data of sunspots from the NASA website. So sunspots essentially varies with the solar cycle. So each solar cycle is of 11 years, and for each solar cycle there is a maxima and a minima of sunspots. So the number of sunspots on the sun changes with each solar cycle, which is why the number of CMEs which are ejected from the sun's corona also changes accordingly. So the number of shock waves reaching the earth also changes. So the histogram is the number of shock waves that my algorithm detected over these solar cycles. So we wanted to plot it against sunspot data to check whether the trend matches the sunspot data, which would essentially mean that it's working. And this is what it looks like. It's a pretty good fit, but there are some deviations that I will explain later. Next. So we also plotted a histogram of the different types of shock waves that we detected. So the red here are fast forward shock waves. The blue is slow forward shock waves. The greens are fast reverse, and the orange are slow reverse. So from literature, we knew that the number of fast forward shock waves are much greater than the number of any other kind of shock waves that reach the earth. So we wanted to also verify that from our algorithm, and this is what we get. Very clearly, the fast forward shock waves are much higher. So here we come to why my plot had some deviations. There are a lot of data gaps from the data that comes in from the spacecraft, and when there are data gaps like this, my algorithm is unable to detect these shock waves as shock waves. So, which is why data gaps like these occur where it does not follow the trend. However, there are certain cases where there are overestimates, which could be due to problems with the algorithm, or they could be due to shock waves that come from other sources, not from sequence alone. So, further work would be to refine our data, our algorithm. Secondly, we want to find an algorithm to detect strong sudden currencies on the earth, which are essentially changes in the DST index of the earth. Whenever a shock wave reaches the earth, it causes a geomagnetic storm, which leads to an increase in the magnetic field of the earth, which is shown as a spike in the DST index. So further work would be to kind of create an algorithm that detects these spikes and find a correlation between the onset of the shock waves and the onset of geomagnetic storms to see if they are related or not. So yes, thank you very much.
Can you just show me your graphs? Back. The order of the noise, at least just first recognizable, but in the rest of the graphs, I don't see that much of a clear indication that there must be something going on. As if you're saying there is a shock wave, but if I consider the bottom one, I mean, there is just a very low as compared to your noises.
Okay, so I'll show you the raw data. So here obviously there's a very clear spike in all three. For temperature there is one, but it's not as clear if you say.
already a spike in all three, we would consider that as a shockwave, and then we refer to other databases that already have been created before. We refer and we see if there actually is a shockwave. Because this is a different way of detecting these shockwaves, and a lot of other research uses stuff like machine learning to train these algorithms to detect shockwaves. So we also want to test that against like our detections. So this is essentially there is a shockwave.
I want to ask you about the choice of threshold. It's very important. How did you decide, and what exactly do they physically approximate?
So whenever there is a shockwave, there is usually a huge jump in the three parameters at least: magnetic field, density, and temperature. That was taken completely from literature. For the velocity, however, what we changed was usually there's a 2.5% jump in velocity that's usually taken from literature. But what my supervisor wanted to do was change that up a little bit, because when there's a shock wave, in the frame of reference of the shock wave, the velocity does not seem to change very much across the continuity. That is from theory, I think. But when we, okay, can I show you another product?
Okay.
Right, so I have this pie chart of shock speed distributions. So I don't think the colors are very clear here, but we realized that there are also a lot of shock waves from the databases that we referred, which have like less than 100 km per second velocities. And also like a lot which also had greater than 500 kilometers, 300, something like that. So all of these were not being incorporated when we put a 2.5% threshold from literature. So we decided to make it 5%.
Let's just go back to your initial drawing. The top thing is
Magnetic.
magnetic field. So you measure magnetic field, you
Oh,
measure velocity,
yes.
you measure
Density.
density, and you measure temperature. So is this the data that you collect? How do you measure magnetic field?
So it's measured on board the spacecraft.
Right.
We just go into the website and ask them.
That I understand. But how does the spacecraft actually measure?
Yeah, I'm not really sure. I think there are instruments on the spacecraft that assist them, but I'm not very sure about it.
Right. So when you now you go back to your just go ahead. I will. Okay. So now this and the previous one.
Okay.
Just tell me what was the difference between what was this graph?
So this graph was when we applied these thresholds.
Thresholds.
Yes.
So now let me just go slowly. I want to see the effect of the threshold. When you go back to that graph, go back to where you are applying the threshold and tell me what part are you not including there. You just said that when you apply the threshold,
Yes.
there is a part that you do not include. And what is the idea of the threshold? The idea of the threshold is
Yeah, it's just to say that this amount of fluctuation means there is a shock.
means there is a shock wave.
Yes.
Right? And you said that you increase the threshold which was typically used from 2.5 to 5.
For the velocity.
For velocity.
Just for velocity.
Just
Rest all is standard.
all the time.
But there could be a completely different phenomena which could be responsible
There
for,
could be. Yes.
and it could also depend upon the part of the cycle that you are observing, sun cycle that you are observing, or the part of the sun cycle that paper would have written.
Correct.
How you can justify increasing the threshold?
The only justification that we had was that because these distribution of shock velocities that I showed you in the pie chart.
But then you are assuming
Yeah.
that whatever
That
distribution
these are
you are getting, these are
CAs.
series.
Yes.
Is there anything else that
Not
behaves like this?
It's not.
Do you do any counterpart measurements? Did you do any counterpart measurements?
So that is also part of our work. I wasn't able to do it, but my PhD student, like the PhD student, was able to do it. But
what counterpart measurements?
so there are co-rotating interaction regions that also cause shock waves that
Yes.
come to the
Yeah.
So I'm not very well versed with that.
Okay, fine.
for his presentation and ask Bhavna, Simran and Nishana to be ready with their presentation.